So let's jump in. So today we're going to be talking about a little bit about microscopy. And so this one on the right is again using a microscope to identify cocaine. Why would you do that if you have all these techniques like liquid chromatography, gas chromatography, all of these other kinds of things? Why would you still use a microscope, you know? And not only that, but the reagent for that test is expensive. It's gold and gold chloride, you know. Can't we save money and do something that's more reasonable, like using an instrumental method and so on? So we'll talk about that a little bit. We'll talk about instrumental concepts not covered in instrumental analysis. Go ahead. And so, you know, we'll talk about the instruments that we cover in 440, but also we'll talk about some of the ones that are relevant to forensic analysis that are not covered in the normal chemistry analytical degree. So we'll talk about microscopes and chemical microscopy. We'll touch on spectroscopy, maybe refresh some of your memory on some of those things. We'll look at elemental analysis and a specific atomic spectroscopy, and then microspectrophotometry. So then we take a spectrometer and attach it to a microscope. So it's a really powerful technique today that's very common. And then hyphenated and 3D techniques. So microscopy is probably the most common forensic tool. You know, put it under the microscope, get a closer look. It makes logical sense. And it uses magnification by the refraction of light. So here's a review of Bragg's law and those kinds of things that you did in instrumental, looking at prisms, looking at gratings, looking at the property of lenses and so on. And we'll see some of these properties today. So this is, again, the speed of light. You may have heard the speed of light is a constant. Well, it's defined. It's the maximum, or you would call it the speed limit of the universe. It's defined in a vacuum, okay? And then when light enters a material like glass, okay, it slows down. So what is slowing light down is its interaction with the material. It also slows down in air, too. So it slows down in anything, in particular, for the light that we're concerned with, it slows down in anything that has electrons. And what has electrons? Pretty much anything, even air, right? So light's going through, and that oscillating electric field interacts with electrons. And so the electrons will oscillate with that field, and they won't absorb it unless there's a particular transition, a difference between the energy levels. Yes? No, it's different by material. And so every material will slow it down differently. Okay. And so air slows it down very little. And so this amount that it slows it down, that changes the speed of the light. So you have this material here, the speed in the vacuum, that's the maximum value. And so if you have a really dense material, like water, then it really slows down. And so you have a high refractive index. So the higher the refractive index, the more that substance slows it down. For air, like this in air is equal to 1.00. I think it's 2 zeros and a 3. It's really, really small. It's a very small difference, right? It doesn't slow it down much at all. But for really accurate work, you'll see lists of vacuum wavelengths. So like if you wanted to talk about like the frequency of a laser, okay, if you wanted to be as accurate as possible, you would list that wavelength of that laser in a vacuum. And then you could correct that wavelength for the laser based on the material that it's going through. So you could correct it for that laser wavelength in air, what its apparent wavelength would be, or in glass, or in any other kind of material like a diamond and so on. We can use this refractive index to then magnify light, to focus it, and so on. And so this is the internal guts of a simple microscope. You have the image plane here that's placed on the camera. Over here you have the object plane. So this is the plane of the object. And this object plane has also a really tight area, depending on the magnification of this focal plane. And you can see this when you're in a microscope. You're trying to focus. You'll see the image looks fuzzy or odd until you get it in that focal plane, and then you can move that focal plane deeper or further back, and you'll see the image change a little bit as it goes. And it's interesting. Sometimes you can look through things. Like you have a cover slip, you have your sample, and you have the bottom of the microscope, and you're zooming in, and you're focused on the dust on the cover slip, and you think, wow, there's nothing here. Well, you're not even looking at your sample. You can't even see your sample, even though your sample's right in line with the beam. You don't see it because the focal plane is not down where your sample is. Okay, and so it always takes some checking at the beginning. You go all the way down and all the way back up and kind of see where all the different planes are in your sample, and so then you can see that the focal these different lenses, they'll take that image. There'll be an intermediate image here. It's typically upside down, and then you'll bring it out here to the image plane. Now you can replace this camera with an eyepiece, and you can put this image plane on your retina. And so that's going through your cornea. And so some of these microscopes, almost all of them, will have some adjustment on one of the eyepieces. And so the procedure is close one eye and get it in focus with the one that doesn't adjust. And so you get it in focus with the eyepiece that's not adjustable, and then you open the other eye. You keep this eye centered. Let's say it's the one that's on the right that's adjustable. You keep this one centered. You close this eye. You get it in focus, and then you open this eye. And if the eye is not positioned horizontally in the correct spot, you can move those eyepieces in and out until you see the image overlay. And then this eye typically needs adjustment. Most of our corneas are not exactly identical, and so then you can adjust this eye till they're both in focus. So this interpupillary distance is an adjustment, and then also the differential focus of your eyes. So it works great. Okay, so this part here is this piece shown down here, this blue piece right here. Okay, and then you have the eye lens, and then you have also the camera that you can attach on the top. Okay. Now the total magnification is the product of all the magnifications. And so if you have a objective magnification listed as 40, that's typically the first number in an objective, and then you have a 10x eyepiece, then you're going to have a 400x total magnification. And then you also have these tube lengths that this is made for. This objective is made for 160 millimeter tube length and a cover slip thickness of 0.17 millimeters. Now, one thing that's super important is whether these objectives are made for air or for oil. Many of these high magnification lenses or objectives are made to work with oil. And so you put an oil drop on top of your sample, and then this fills this gap here. And so that can change this numerical aperture quite a bit. So see this A here has to deal with this refractive index of this gap here. And so if we want to resolve smaller features, then we want to increase this numerical aperture. And we can do that by putting oil or something with a high refractive index in this gap. Okay. So let's look at that. We have these different resolving powers. We want small resolving powers. We want to resolve the smallest features possible. So here I've got this this lens with a numerical aperture of 1.3, and we have the sort of middle of the visible range if we're looking at with our eyes or with a camera, 550 nanometers, and we can see that the resolving power might be 254 nanometers. So these two items could be that close together and we would still see a gap between them. So that's what we're looking at. So this would be, if you were to plot this, you would see, the object, and it would be baseline resolved, and then you would see the next object. If we use this oil immersion lens in air, then it's this resolving power is proportional to 1 over the refractive index, and so we would see then our resolving power has been reduced. It means it's the higher number. It can resolve objects not as close together. And so here we might, if we were to plot these objects, we might see the object and then it would only be, say, 50% resolved. Now we have a lot of choices in terms of the refractive indices of these oils here. And so look at these different substances over here. Air, okay, I was off by 1 zero. It's 1.0003. Told you it was very small for air. But then look at water, 1.3. Then we have glycerin, paraffin oil, cedar wood, synthetic oil, and all of that. We have all of these different, with the biggest being methylene iodide. You see these iodines and bromines. They really increase the refractive index. Why might that be? Why would you expect iodine and bromine to have such a high refractive index? I want you to try to get some intuition about this. Not the electronegativity. The first part, yes. Yes, so it's the electrons that are interacting with light and slowing it down. So if you've got a big old fluffy bromine, then light comes through. Think about how far out those electrons are in the bromine. I don't know if you had me for PChem, we talked about the size of a hydrogen atom. If that red ball at target was the nucleus, was a proton, then the hydrogen atom was from Spring to Madisonville, or from Livingston over to Navasota. So that's how big a hydrogen is, with just one electron. Sodium was about the size of Texas. Okay, bromine's even bigger than that. So the bigger those atoms are, the more fluffy their electrons are. And so when light comes in, it really slows down in a bromine or an iodine atom. Okay, and so they have a really high refractive index. Now what's interesting with these refractive indices, I know this slide says polarized light microscopy, but let's pause for a second and let's look if we had bright field illumination. We might see this crystal. I'll try to draw it on here. Okay. And so notice how the background is bright. You see that? And we see the edges of the crystal. They're only visible if there's a difference between the refractive index. So like N equals, let's do air, right? 1.0003, and this was 1. Let's say 4, or let's do water. So 1.333. So we've got a crystal that has the refractive index that's very close to water. That doesn't mean it's soluble in water. I'm just saying it has a refractive index that would slow light down, the same as water does. Okay, and it's in our field of view, and we're letting all the light through, and we can see the edge of that crystal. The reason we see the edge of that crystal is because when light gets really close to the edge of that crystal, it hits the edge of the crystal and really gets diverted into the crystal because it slows down and gets pulled into the crystal. The light that's just a hair to the right of that goes straight through air and hits our lens. So the edges, because of the refractive index difference, the edges really steer a lot of light, so they appear black. So they either reflect it and it bounces off, or they steer it into the crystal. And so right at the edges, if there's a difference in refractive index, light gets steered into the crystal or bounced off, and so we see a dark edge around glass or crystal that's clear. This could be a clear substance, put it in light, all this white light's coming through. How is it that you can see the edges of that object? It's because of the refractive index. Let's test this. So if we put this in water, this is what we see. We might see a little hint that there's an edge there, but if it's a perfect match, so N equals 1.333 and N equals 1.333, the edges disappear. And so you can use this technique. That's why we have this little kit of all these different refractive index oils. Let's say you have a piece of glass from a car crash or something. You have a headlamp. You can pull that in and you can do a non-destructive test in microscopy with these different index matched oils. And when you match the refractive index of that little glass chunk, it'll disappear, which is pretty neat because light's not steered by the edges. It's in something like water, it's going along, it's slowed down by 1.333, and it hits the edge of that glass. It's still slowed down by 1.333, so it doesn't steer to the left or the right. It's not refracted or reflected off. And so the only reason light bounces is because of a change in refractive index. So all of your windows, when you see a reflection in the window, it's because light's going really fast through air. It hits that window and it either slows down and goes into the window or it bounces off. And then you get a reflection. So that's also why you don't see, like if you're scuba diving, and you've got your glass there and water's touching that glass, light, you don't see that second surface. You might see something reflected in the first surface, but you don't see anything in the water to glass interface. So what we're doing here is we're playing with contrast. So contrast is the key to microscopy. And so one of the things we can do is if we have a specimen that rotates light, and so how would a specimen rotate plane polarized light? It might have a refractive index that, let's pick this. See these two arrows here? One is longer than the other. So we could say Nx is equal to 1.3, Ny is equal to 1.5. Okay, so that means it's anisotropic. Isotropic means it would be the same in all directions. But if light is along the x-axis, it's going to slow down more than if it's on the y-axis, or vice versa, however I've got it written. I think the y-axis is slower. Okay, and so that's strange. But if we have that situation, light will rotate when it goes into that substance, okay? Because it can go faster at a different angle. Okay, so when it goes through, it'll rotate its way, and not only that, but it's wavelength dependent. So blue light will rotate differently than red light, and so we can get colors out of this and so on. If you have an isotropic substance, notice down here this polarizer lets only, we'll say horizontal, or we'll say this is X. So X polarized light through. So you see all we have going into the sample is X polarized light. If it's isotropic, it doesn't rotate that plane polarization. And now what we have on the detector is Y polarized light. Well, that's going to cancel all of this X polarized light. And so we don't see anything. And a lot of times this is called dark field illumination. You've got a dark field. You don't see any light coming through. So if the sample doesn't move or rotate light, you're not going to see anything. Now that's information that tells you that substance is isotropic, not anisotropic. Okay. But then if you have something that does rotate the light, look at this. We've taken that crystal, and if we turn the crystal, then it will rotate light a little bit. And so it starts out X polarized, and then it is rotated a little bit. So now it's turned the light a little bit, and some of that light will have a Y component, and it can get through. And so then we have this crystal that glows in the dark, if you will. It's not really glowing, it's rotating light and letting it through. So let's just look at some of these crystals. This is out of my lab. We did some precipitation experiments with 4-nitroaniline in different solvents. And you can see the dark field in the back. and then the crystals just show up. Beautiful. Okay. You can get a feel for the depth of the crystal too, how thick it is, by looking at the different colors. And so you can see here, this has got a green spot in the middle and it's pink on the outside. It has nothing to do with the color of the crystal. These crystals were all yellow. Okay, so how is it that we're getting green and pink light through? Okay, it's because the white light's entering this crystal and it's being rotated. And so the green light's going around a certain speed and the pink light's going around at a different speed. And when it hits the other surface, if it's changing color as it goes, you've got a mixture of green and pink as it's going through. It's going to alternate between green and pink. It hits a certain thickness and the green light escapes. If it goes a little further, that light turns into more pink light and it escapes. And so we see different colors based on the thickness. And so you can see that in this big plate-like crystal here, it had a little bit of solvent still on the surface. And then when these crystals were filtered, then that solvent left a pothole, if you will. Okay. And so when that solvent evaporated, we had this little pothole in our crystal, and we see a different color there. You can see here, this has like a shelf, and that shelf is chipped off in this end of the crystal here. Okay. But the main point of this is to capture the shapes of the crystals, maybe then measure them. We've got the length to width ratio. So this would be the length. This would be the width, obviously. So these are like needles when you've got a really narrow width and a long length. This is more like a plate. And that's what we were doing. We were trying to change the different solvents to see if we could change what's called the crystal morphology, or the form of the crystals. Do we get more needles when we use this solvent? Do we get plates when we use that solvent? Do we get gravel where everything just precipitates out so fast it's all microscopic? But the point is we use this to increase, the point is to increase contrast. That's the goal. So then we can then make measurements of the crystals. Okay, let's look at spectroscopic terms and review some of that. This is, light's coming in, it hits the sample, we get transmittance. Let's do transmittance first because it's easy. Take the sample out and you get the source, source light or reference. And that ratio tells us transmittance. Okay. And that is equal to 10 to the minus absorbance. And so it's the absorbance term that's proportional to concentration. So I'd really like everybody to commit that to memory. So this is, C is our concentration. B is, y'all tell me, what is B? Path length. And this epsilon, absorptivity is a good way to think of it. Yeah. And I'll just leave it at absorptivity. If the concentration is in molarity, then it's the molar absorptivity, but it could be in any other units too. It's just that function of that substance that is absorbing light. So that's it's sort of its native absorption, and then you add in the path length, and then you add in the concentration units. But notice it's log based, and so absorbance is equal to the minus log of I over I naught. Now, we could do reflectance too. And so if we were able to measure I naught coming in here, we could have the reflectance too. And we could take the minus log of that, and we could have the minus log of the reflectance. We call this R. And there's really not a name for that. We have absorbance, but but we don't really have a term. This is like absorbance, but it's not absorbance because we're dealing with a reflectance, not transmittance. So this is common. We would use this term here, and we would just list it as log R reflectance. Now, if it enters the material at certain angles, we might get internal reflectance. It doesn't happen at all angles, but there's what you call magic angles. It comes in, and like in a fiber optic, the light is inside that fiber optic, and you have internal reflectance all the way down the fiber optic. So if you get, like I do at the house, fiber optic internet, they bring the signal light into that fiber at the right angle so that it enhances internal reflectance, and then it can travel for miles. Let's talk about these two. These are important for specular reflectance and diffuse reflectance in terms of characterizing the color of substances. So specular reflectance gives info about the source. Diffuse reflectance info about the sample. So let me see if I can. Can you see a reflection in this board of, say, the window? Let me open this window. Can you see the trees and the blue sky a little bit over here with this smooth board? Because this board is smooth, you get a lot of specular reflectance. Okay, and notice how the angle is preserved. It has to come in the window, hit that board, and come off at the same angle to the normal. The normal of the board is here, and you've got, say, 30 degrees from the window hitting the board, and then 30 degrees over this way is going to be the image of that window. That's specular reflectance. And you can tell it's giving you information about the source because when you look at it, you can see trees and cars and the blue sky. Okay? It also measures how rough the board is. If that were a mirror, then you have almost perfect specular reflectance. You get all the information about the source and nothing about the substance. I have no idea what a mirror is made of by looking at it, but I can tell a lot about the source. So specular reflectance is about the source. It gives you more information about the source. It does tell you about the roughness of the mirror. Okay, if it's frosted glass, it's not a very good mirror. Okay, so you can learn something about the substrate, but you can't really learn much about the color of the substrate or the sample. Okay, it's diffuse reflectance that gives you the color of the sample. Okay, so it's the angles other than that special angle. So notice these angles are all at different angles. They're not preserving this angle here. So this is the normal angle of incidence that gives you specular reflectance. All other angles give you the diffuse reflectance. And so if I were wanting to see, something about the board, the color of the board, I would not want to look, say, at a bright source that was illuminating it. I would want to look at a different angle. Okay. And then we have absorption and transmission shown on here too. Okay, let's look at instruments. We've got two types of instruments that we typically use: dispersive instruments, and then diode array, or grating and prism instruments that scan. So these would be scanned versus fixed. So let's look at these two pieces right here first. Diode array. So a diode array instrument, they've become very cheap because of camera technology. So as we've gotten really good at making sensing elements for cameras and making them smaller and smaller and smaller, more and more megapixels per square centimeter, then our spectroscopic instruments have gotten really cheap, especially in the visible range, because our camera elements are made to respond to visible light. And so now we can make these USB spectrometers that, they fit on looks like a USB drive with a fiber optic coming out. This is great for field studies. We make handheld Raman spectrometers now that use visible lasers that can go into the field and can be battery powered because of the camera technology. Those would all be diode array instruments. And so more resolution requires more pixels. And so you have, this is the sort of the camera detecting or sensor element. The other nice thing about a diode array instrument is that it has a fixed grating or a fixed prism. The dispersing element is fixed, so there's no moving parts. Now, if you want high resolution, you need narrow slits. So you need to take the source image and make it really, really narrow so that when the grating disperses it, you have, as close to single wavelengths of light coming out onto the camera element. And so that reduces the amount of light hitting the camera element. So in order to see anything, to get any signal in a reasonable amount of time, you have to turn up the voltage on that camera element and you get a lot of noise. So these instruments at high resolution can be very noisy, and so that's a trade-off. Okay. Now for a scanning instrument, notice we have a really sensitive detector. Which means it can see very minuscule amounts of light. And so we can narrow the slits way down. We can have a noise-free spectrum, but it's very slow. So slow scans are a problem for scanning instruments if we want high resolution. So you just have to, and also you have moving parts, and so it's not a very robust thing. You have a motor that turns the grating or the prism really, really slowly, and so then that motor requires power and so on, and so these things are less robust too for field work. Now, how do we discuss resolution? Let's talk about the peaks. Spectral bandwidth is an important piece. And so you'll see this FWHM as an indicator of the resolution of an instrument or the width of a peak. That's the full width at half maximum. And a lot of times, like in PCHEM, we modeled our spectra with the Gaussian peak shape. And I didn't really get into it much in PCHEM that the sigma, the standard deviation that you use for a Gaussian peak shape here, is not the full width at half maximum. They're related to each other, but the full width at half maximum is this sigma times 2 times the square root of 2 log 2. So it has all of these 2's in it. But anyway, this is related to the standard deviation of a Gaussian or normal distribution, but it's not exactly the same. Okay. Another problem with spectrometers, especially cheap ones, how many people have used the Spec 20? Everybody? What class was that used in? Biochem? Okay. Was it also in Gen Chem 2? The copper solution, copper sulfate? Yeah, that's right. Those are the ones I'm talking about. The ones in Gen Chem were pretty, I mean, it's that we don't have a lot of money to spend on that many little instruments and so on. So they have a problem with drifting. So let's talk about the Spec 20, where you've got just a single box, you've got the light, you've got a little cuvette holder, and you've got your detector. And so you put the blank in there. Say if you're doing copper sulfate, you put water in there in the cuvette, and you adjust the little needle so it says 100% transmittance, or let's say 0% absorbance. We'll do that, and then you take the cuvette out and you put your sample in. But at the same time you put the sample in, some kind of power surge or something happens, or the elevator's running or whatever, and so the light gets dimmer, not from the sample, but because of the electricity. And so it drifts. And so this is drift. We don't want drift. And so if we look down here, notice this top line is going along strong. Let's say the elevator is going, and then all of a sudden they reach the floor, and the power of the building comes back up, and now it's up here. You see how the signal's drifting? That's moving our baseline. And so that's changing all our blank signals and moving where we set it to 0 absorbance. That's a problem because now that's no longer accurate. And so one way to correct for signal drift is to have two paths in our spectrometer. So we've got our source here, and we send some of the light through a reference cell, some of the light through a sample cell. Now, that's pretty inexpensive. Mirrors are pretty inexpensive. The thing that is expensive is the detector and the monochromator. So we don't want to just have dual paths that have 2 detectors and 2 monochromators. For one thing, it's hard to get 2 detectors to give you the same amount of signals. So you'd have to correct for 2 different detectors. Okay, monochromators too. So it'd be nice to just have 1 monochromator and 1 detector, but we've got 2 beams of light. So how do we get them to go through the same monochromator and the same detector? We use this thing called a chopper. It looks like a fan, but it's really not bladed like that. It's got rotating segmented mirror. So this mirrored surface, if we were to look straight on, it would look like this. So this is mirrored, and this is clear. And then we just put it at the correct angle so that it reflects the sample light into the monochromator. And so we just angle this mirror so that light either goes through it from the reference cell or from the sample cell. So it'll block the reference cell and send the sample through, and then it'll rotate a little bit, and then the sample light goes through this way into a dump. Okay, we just dump that signal, and then the reference goes through. So when it's clear, they cross, and when it's mirrored, the reference gets blocked by the mirror and the sample gets reflected. So it's basically really quickly chopping the signal into reference sample. So what you would do if you had a Spec 20 and you were trying to do this, you would do this 1,000 times a second, 1,000 hertz. Blank, reference, blank, reference, blank, reference. So that's what it's doing for you at really fast speeds. So if you were to plot this out by time, then you would see, this up here is I naught, and then this down here is I. And so you're plotting along. So if you're also scanning the wavelength, so you're scanning the wavelength in time too, then you would see that this is a peak here, and then this is a peak. This might be a sharp peak, okay, and then some smaller peaks like this. So that's your spectrum. And then this chopper, because the source is drifting, okay, all of that is set to 100%, and so then you get a nice clean spectrum with this flat baseline at 100%, or a transmittance of 1. So that's a way to correct for signal drift. That's really important. Many spectrometers will have choppers. This would be for a scanning instrument. Okay, I guess you could use it also for a diode array. Yeah. And then let's get into getting rid of slits. And so in this case, we would have a slit that lets just a portion of the light through. It might even be before our sample and reference. So there's different places you can put it in the spectrometer. And what that does is severely restricts the amount of light going through our instrument. So we have to turn up the gain on our detectors, which introduces noise, or we have to look for a really long time to sort of add up the amount of light that's hitting our detector or counted by our detector. This is a way to get around that. This is interferometry. So notice this is one of the biggest features of an interferometer, that there are no slits. 100% of the light goes through. You could think of it as a resonant cavity for light. So light comes in, 100% here, 50% goes up to a fixed mirror, the other 50% goes through to a moving mirror. We move that mirror back and forth, and it interferes when it comes back to this beam splitter. It interferes with itself. And if these distances are the same distance, then we get 100% of light out. So to the detector, it looks like a mirror. So it looks like there's just a mirror there, and the source hits that mirror and comes down to the detector. But it's actually a resonant cavity, and we can detune that cavity by moving one of the mirrors. And so when we detune it, we sort of select which light is going to be reflected efficiently and which light is not. So there creates this difference between the path lengths, which causes interference between certain wavelengths of light. And so that's why it's called an interferometer. So we get this complicated pattern of light out of these devices, and we do it for the blank or the reference, and then we do it again for the sample. So in this case, this would be a single beam instrument, and so we have to run a background, store it, and then we run a sample, and we do the ratio. So if we wanted to know how long X needs to be for 4 wave number resolution, say in the infrared, this is the equation here that we can use. Okay, we can solve for X max. So 1/2 times the delta nu, the resolution we want. So if we had 4 wave number resolution, okay, then we would need a 2.5 centimeter path length. So that's not very far, 2.5 centimeters, it's 1 inch. So our interferometer can get 4 wave number resolution very easily. In graduate school, I wanted 1,000th of a wave number resolution for my thesis research. And so I needed a spectrometer with 5 meters of a path length for this. And Bruker makes one of those. They had it at the National Laboratory up in Pacific Northwest. And so this is their instrument. They had the Bruker 125 HR, the highest resolution FTIR. And it had this 5-meter interferometer. This thing was so long. It basically went from where that trash can is all the way to the wall. So the spectrometer was down there at the end. It was kind of a small spectrometer. I mean, maybe the size of this bench. But then the interferometer was 5 meters long. Yeah, it was fantastic. Okay. Took a long time to take a scan because you had to move that mirror down and back. It had a little track and a cable that pulled it back and forth. This is the spectrometer we use in my lab. It's got the source here. Here's the interferometer. Then the light goes through the sample, and then it is reflected onto the detector. So those are your main parts. We can hook this thing up to a microscope and do microspectrophotometry. So the microspectrophotometry. So these are different pieces. The micro part means the microscope. Spectro means we have dispersion of light. And the photometry is measuring the intensity. Essentially Beer's law. A equals EBC. So whenever we're calculating the concentration, that's the photometry, the measurement of the photons that come through. Whenever we're measuring the wavelengths, like an infrared spectrum, and we want to say, oh, it's a carbonyl, oh, it's got a CH stretch at 3000, oh, maybe there's something down at 700 wave numbers indicating, I don't know, carbon-carbon bonds or a carbon-chlorine bond or whatever. That's looking at the x-axis, right? So that's the wavelength axis or the wave number axis. That's just spectroscopy. So we're using the spectrometer as a spectroscope. We're looking at the wavelengths. When we're dealing with the y-axis, we're measuring the intensity. We're looking at the number of photons. We're doing Beer's law. That's spectrophotometry. So microspectrophotometry or microspectroscopy. Spectroscopy would be looking at the x-axis, identifying certain compounds based on their positions of their peaks. The intensity of those peaks would be photometry. And then we have the attenuated total reflectance attachment to the infrared. So what's the total reflection piece is this piece right here. The light from the interferometer is 100% reflected. Because it's at the right angle to do that, the correct angle. It's not a right angle, it's a correct angle. Okay. But if we put a sample on the other side of that, now remember what I said earlier, what's causing that reflection? Let's see if we can review from 30 minutes ago. What's causing it to reflect? That's the type of reflection. That's exactly right. It's the type of reflection. But something, so it's in particular, in ours upstairs, it's a diamond. So this substance right here is a diamond. And so light's in diamond, and it's coming up, and then it's reflecting. What's making it actually reflect? The change in refractive index. So it's the change in refractive index at the surface of that diamond. Even though you're inside the diamond, you're getting an internal reflection. Okay? You can put, so what's happening at that surface? So think about that surface as this pool of electrons that are in the diamond structure, and light is bouncing off that surface. That surface is going to be bouncing, right? Like this. So that diamond surface, as light's hitting it, is bouncing. If you can put your sample really close to that surface, you might be able to steal some photons of light because that surface is vibrating at the same frequency as the light is. And so that's the attenuated part. So attenuation is a diminishing. Diminished total reflection. So it's not total reflection. It would be if there's no sample there. But if you put a sample there, you can diminish it in certain frequencies. And just like you see the two different frequencies, the cat has a higher frequency than the little girl. Okay. And so you'll get absorptions of low frequency motions with a big chlorine or carbon-carbon stretch, or the CH stretch will be really high frequency because it's light, like this cat. Okay. Now you've got to get it really close to the surface because this doesn't leave the diamond. That's the thing that's weird. It's called an evanescent wave. It's sort of a hidden wave above that diamond. So you've got to get your sample as close to that surface as possible, which is why we have a press. We press it down. So if you just put a loose powder on top of that diamond, you might have the 2 or 3 particles that are sitting on top of the trampoline, but all the other stuff is pretty far away, and the effect isn't going to happen. So you got to press it down, smash it against that surface so that they can feel the vibration of the electron cloud. Okay. The problem with this is that the ATR effect, this evanescent wave, this bouncing on the trampoline, is wavelength dependent. So we don't have a fixed path length. For transmittance, it's very easy. You got a 1 centimeter cuvette. So the path length is 1 centimeter. For the ATR, it's not fixed. What I've got plotted here is the path length or the depth of penetration of that wave for a normal, like, organic substance. So it's based on the refractive index of the sample and the refractive index of the crystal. And so for organic substances, up here in the CH stretch region, our path is zero point 0.2 microns. That's not very much at all, okay? But down here, for like the path here for the low frequency modes is, 1.3 microns. So six and a half times higher. So it's going 6.5 times deeper at 500 wave numbers than it is at 4,000 wave numbers. And this can shift your peaks. Let's say you had a peak that was centered. If you were to do this in transmittance mode or absorbance mode, your peak comes in at 1400. If you put that peak on a sloping baseline, it can shift by quite a bit. That exact same peak centered at 1400, when put on this shifting baseline, it raises this side of that peak on the low end side so that it looks like it shifts to the left. And so the peak maximum would be shown at 1390. And this can be early on. This faced some, it doesn't really now, but it faced an obstacle in court because our databases were absorbance. So the old ones. We had old databases and transmittance that could be converted in absorbance without any shifting. But then if we took spectra using the ATR and compared it to a database that used absorbance, the peaks didn't line up. They were off a little bit. And so then you could say, well, you said this peak should have been at 1400 for drug X, and your spectrum shows it as at 1390. Those are not the same number. And you say, well, phooey. So what they had to do is just go back and recollect all of the drug spectra using the ATR. So it's important, if you're going to use an ATR attachment, you should use an ATR database so that the peaks line up the best. Okay, there are other spectroscopic techniques, that UV-Vis, AAS, which is atomic absorption spectroscopy, FTIR, and Raman. These are not really different than what you learned in instrumental analysis. But let's look at some of these others that were not as well covered in instrumental analysis, like X-ray fluorescence, scanning electron microscopy with wavelength or energy dispersive detection, and then electron spectroscopy for chemical analysis, or ESCA. So this is using the core electrons. So the refractive index, light's coming in, it's really interacting with those electrons that are farthest from the nucleus. Those are your valence electrons. But what about the core electrons? If you hit it with X-ray light, you can get a photoelectric effect. So the X-ray photon comes and hits this electron and kicks it out. So this is a photoelectron. Now there's a hole in the 1s orbital. And so those other electrons are not going to sit in the 2s orbital or the 2p orbital when there's a place really close to a very positive nucleus. And so they're going to jump down into that seat. Okay? It's like the prime location. This is front and center, front of the television. So they're going to jump down and they're going to kick out emitted X-rays. So this is X-ray fluorescence. This is the fluorescence signal. Just like we have fluorescence in the visible region, if we did increasing wavelength, so we would have the incident light, I0, and then the fluorescence, I fluorescence, emitted. And it's red shifted, right? Because the incoming X-ray was enough energy to kick the electron completely out of the atom. So that's got to be really short wavelength. The longer wavelength would be electrons just jumping from the 2 shell or the 3 shell. So again, that's not from the outside world, that's just within the atom, so it's got to be longer wavelength. This is great for trace detection of elements. Now, how do we get, we don't have to use an X-ray. this X-ray here, we could also use, we could kick out an electron by hitting it with electrons. And so if we have a scanning electron microscope, way up here we've got a hot wire. And those electrons could come streaming off of this. And then we can use negatively charged rings and we can focus those electrons and treat them like optics. So this is electron optics or scanning lenses. They're not glass lenses. They're just little rings that we can very accurately set their charges. So we can charge those up negatively, and these electrons that are negatively charged will be repelled by them, and we can focus them at will. We can scan them around and so on. And so we blast the surface with these electrons. If they go through the sample, if the sample is really narrow, then we can get transmitted electron microscopy, TEM. If they bounce off, we can get backscattered electrons, and we can get an image that way too if we scan or raster the beam across the top. And then the electrons can scare off. So you've got a core you've got a nucleus here, and you've got electrons in the core. We'll just use the Bohr model to show our little electrons. And we've got an electron here that's coming in incredibly high energy, and it scares off that electron, ejects it. So we can knock out core electrons with electrons, and then we can get the X-ray light out. So that's what these X-ray photons coming out. They have signal very similar to X-ray fluorescence, but we didn't hit it with X-rays. We hit it with high energy electrons. And if we detect that, we could disperse that electron by energy or wavelength, and we get energy or wavelength dispersive X-ray analysis. That's what we use for gunshot residue. So when we get to that section, we'll be talking about this scanning electron microscopy detection of X-rays. Now, if we raster this across the surface, y'all haven't seen these old TVs, have you? These cathode ray tubes, you know, your grandparents' TV, the one I grew up with. Okay, it's actually scanning an electron beam at that glass that displays the image. And so we could take that same kind of element here and put it in our scanning electron microscope, and that's the scanning part, and we could just scan those electrons across the surface and look at how many electrons bounce off and hit our detector. And you can produce an image that way. Now, the one problem with this is, notice we're throwing electrons at our sample, a lot of electrons at our sample. What if our sample doesn't conduct electricity? So electrons hit our sample, maybe it knocks some of them off and our sample becomes positive, but more likely our sample starts to capture electrons and becomes negative. So as we're spraying electrons across the surface, you could have some positive spots, some negative spots, and if you don't have a conductive sample, the positives and the negatives can't communicate, they can't cancel each other out, so the surface charges up. Okay. And so then your image gets crummy because you're trying to send an electron at a negatively charged thing. At first it wasn't charged, now it's charged, and the beam gets steered away by the positive charge. And so it starts to deflect our beam. Have you ever seen an Olympic swimming pool with the stripes, you know, a competitive swimming pool with the stripes and the lane markers before anybody gets in? You can see perfectly, you can see the straight lines, you can see the tile on the bottom, you can see all of that. That's when your sample's not charged. Somebody starts jumping in and changing the waves, what happens to those stripes? They start to get all wiggly. You can't see the fine images of the tile or anything anymore because you've got such a distorted image. That's what sample charging looks like. So when you take a quick image in the scanning electron microscope of a sample that doesn't conduct electricity, the very first image is going to be your best image. And as soon as the sample starts to charge up, it looks like the bottom of a swimming pool after people have been playing in it for a while. Okay. So this is a problem. And the way we get around that is we take our sample, we put it in an oven, or like a vacuum chamber, And then we have a hot gold wire above that. Is we pull a vacuum on it, and then we heat up that gold wire, and gold will come spewing off of that wire, and it will coat our sample. Or we can do it with carbon, like graphite, but gold is very common. So you have a little gold coating machine. You put your sample in there, you coat it with gold. A very, very small layer of gold, not enough to change the sample, not enough to destroy the sample, but enough to conduct those electrons away. And then you put it in your instrument, and you get a scanning image of it. The X-rays just come from those open 1s electron spots. The outer electrons jump down and give you the X-rays. So again, that gold coating for SEM is destructive. It's changing the sample. So you want to make sure that if you're going to have to gold coat something and get an image of it, that's the last step that you do. Then we have some other techniques that aren't covered at all in chemistry departments. Typically, you've heard of obviously you've heard of mass spectrometry, different types, ion trap, time of flight, all those different things. This is ion mobility spectrometry. It's not a mass spectrometer, it's an ion mobility spectrometer, because there's not a vacuum in here. There's a counterflow of air. So in this chamber, and this is what they use at the airports. Maybe you've seen this particular instrument at the airports. They swab your luggage with a little linen cloth, and then they stick that sample right here, and they blow hot air through it, okay? And so they swab your luggage with this little tab, and so this is the area that touched your luggage. They put it in here, and the molecules come up here, and they get ionized in this nickel 63 source, and then they're attracted to this collector or detector. Now, the thing that makes this different than a mass spec is that we have a counterflow of air. Look at this arrow here. So air is coming in here with a really inexpensive air pump. You don't need a vacuum pump. Just pump air through here. And the molecules have to go through that air to get to the detector. And then these rings, because our particles are charged, these rings just keep the particles from drifting off. I like to think of this as a dance floor. So the molecules are trying to go through air to get to the detector. And have you ever been to a dance? I don't know if people do that anymore. If you're at one side of the dance floor and you've got a little kid who's about 6, real energetic, and you both want to get to the other side of the dance floor, you're probably going to get there at different times. The kid's probably going to be faster, okay, because they can zip between the legs and so on. And you're more polite, okay? You got a bigger electron cloud, so you're like, excuse me, But that's what this is. It's not mass spectrometry, it's mobility spectrometry. And so the ions are differently mobile in air, counterflow of air. This is the type of signal we get. We get this, what's called a waterfall plot. It has a built-in calibration, and so this very first spectrum here is the calibration gas. They've been using dichloromethane for a long time, but this is the cal. It's a gas that's easily charged by that source. And so what happens is your molecule actually comes in and it bumps into the calibration gas that's negatively charged or positively charged, and it either donates or steals an electron from your sample. And so then it's the calibration gas that charges your sample. And then you get this. You see how this stable signal is developed. You get a total amplitude, you get a width, and you get a maximum, like this would be the maximum of your sample. And they've done standards. They know heroin and cocaine and TNT and nitroglycerin, all the different explosives and all the different drugs. The Coast Guard really developed this technique for detecting drugs on boats. They would board a boat, they'd swab all the different places, and they would run it on this very quickly to see if they had probable cause to search the vehicle or the vessel. And so they had it tuned for drugs. And then with airport security after 9/11, they said, let's start converting this over to explosive detection. And so they switched the detectors and so on. And now it's more sensitive for explosives, and that's what they're detecting at the airports typically. All right, lastly, let's switch gears and go back over to chromatography. We talked a little bit about that last time. And in the instrumental class, I'm not sure they talk much about derivatization. So this is a key piece of the puzzle for problem analytes, and in particular acids. Okay, so H bonding or hydrogen bonding analytes bind too strongly to a normal phase, which means they take too long to elute. And so you don't want your chromatogram to give you all of these peaks, and then you wait for 10 or 15 minutes, and then this really broad peak comes out, and that's an acid. Because it really stuck to that stationary phase, and it just drug itself along, and that gives it a chance to really broaden out. The longer something's on the column, the broader its peak becomes. And so you would like for your acids to come out quickly like all the other less polar analytes. And so they have these things called derivatizing agents. So this is an example structure of the sialization. So you have a silicon with a chloride on there that reacts with an acid or an alcohol and puts this very nonpolar group on your acid. And so then it comes out here with all of the other nonpolar substances. And so you've moved your acid over here. Another great thing too is you've added a silicon. That's great for mass spec. Okay, here you've added fluorines. Also great for mass spec. Okay, so if you can put a derivatization element, that species on your acids and alcohols that have things like fluorine or things like silicon that are less common in drugs of abuse and so on. There's not a lot of drugs that are based on silicon chemistry, right? So you stick a silicon on there, it's like a big bright light when it goes into the mass spec because the silicon is so much heavier. So you'll get this silicon signal that tells you that it interacted with this acid that was in your unknown. And so this is a new technique, or a technique used to enhance gas chromatography and mass spec. And then here's the last little diagram here. This is a general guide to the types of column selection in chromatography. So for small molecules, things that weigh less than 1,000 grams per mole, we can use partition chromatography, which uses reverse phase or normal phase. So this is your regular GC and LC. Then you have ion exchange if you have ions. You have adsorption if you have permanent gases. And then for the higher molecular weights, these are for your polymers. And so this is just a list of all the different types of names of types of chromatography. All right. And then just some other terms. There's a Kahoot that we'll probably do at the beginning of next class so that you guys can start studying again. And we'll go over just some of these other things. But these are some of the terms that we had in the text that we covered today.